Hello and welcome, everyone. Today we have something very special for you. We thought that the talks on the Rust Game Dev Meetup are a little bit short and wide in topics. So we prepared a new meetup, and this is the test pilot for it, where we're going to talk more about graphics, more technical, and longer talk to be able to explore the topics deeper. I appreciate everyone tuning in, and hopefully this is going to go great. Just a note that this is not about gfx-rs. This is the general Rust Graphics Meetup. We have a code of conduct, which is the same as Rust code of conduct. So please be friendly. And we have 3 speakers today. Myself starting first, and we'll hear Connor talking about the Ren 3, and then Andreas talking about the interactive GPU fluid solver. And Forrest organized threads in the meetup chat where you can join and ask questions. So please do that. And with this, I'm going to dive into the first talk, which is about gfx-rs. We have a lot of exciting stuff coming, and looking at the past is something we should do first. So it's called lessons learned. Because gfx-rs today is basically abandoned. It's in maintenance mode. Let's see what we can learn from it. gfx-rs started in 2014, a year before Rust was even 1.0. It started inspired by the production level engines that we had some idea of how they work, and before any of the next-gen APIs showed up. It started with the idea that we can move the talking to the low-level API to a separate thread even, or isolate it somehow. And that idea quickly evolved, and gfx-rs became nothing like it started. First, we call it the Prelow level, which lasted for 4 years. And the general idea was that let's use the power of Rust to minimize the chance of errors. So we would have the user specifying the vertex layout, the resource bindings, and render targets at the strong types, so that we can enforce that and make sure everything is smooth. To do that, we looked for different ways. We found macros to be most appropriate. So we would have a big define with a lot of different things, like the vertex format you can see here, and the pipeline with everything in it. Vertex buffers, the output colors, all the uniforms, everything goes into the pipeline. There is also fancy syntax for initialization, and separately, the user would create the data instantiation where they provide actual buffers. As a result, we had these 3 different things, the definition, initialization, and data, and users were constantly confused. What's the difference between them and how to use them? They would just blindly follow the examples at best. Macros are difficult for everybody, especially for tooling, because it was early days, difficult for debugging and reading, and it's just some magic syntax on top of the language. So our first lesson is, please stay away from macros. Maybe they're better today, but at the point, I think choosing macros was not the best decision. Then we had this interesting idea of stateless. gfx was described as a stateless API. And I was particularly proud of it because the idea was that you take all of the dependencies of your draw calls and you specify them each time you do a draw. So there is never a case where a state is getting leaked and accidentally there is something drawn wrong. Or at least we thought that there is no chance to do that because the user has to specify it, right? What can go wrong? So guess what happened? It's just that responsibility for leaking state got shifted to the users instead of the library. And that's not even the worst. The worst is that users were thinking about passes and thinking about the number of things they want to draw and they would build those states and basically mutate them in their code, effectively doing the same thing as we would do, but then our code had to deduplicate the state and figure out the difference between what needs to be changed and what was the same. And then it introduced overhead. It introduced the, it wasn't obvious how much work is going to be with each draw. For example, you could have each draw with a separate render target, and changing render targets is expensive everywhere. So we basically shifted responsibility to the user. And it's not a great API that just avoids responsibility. A great API should pave the way to solve the problem. So pave the way to success, not just shift the responsibility to the user. So lesson number 2, just avoiding responsibility is not the best way. Taking responsibility the right way is the best. And also, the computer graphics is inherently stateful. I think this is a bit of a controversial topic, but that's my lesson from it is the good API should expose the state in a way that's good rather than try to avoid it. And one of the ways I thought would be interesting to look today is something like Luminance that did it. It's a stack-based approach. Then we were asked, okay, I can't specify this at compile time. Can I specify this at runtime? And we had this powerful trade system that allow you to trade off between runtime and compile time. And we built the data layer, the raw API on top of it, allowing users to specify that runtime, but it was running on top of the same trades. Wonderful, right? Yeah, we did it just because we were just too deep in this approach to change direction. And the result is people were even more confused as to how this worked. There's just a lot of magic going on. So lesson number 3 that we have is the types have to be built gradually on top of your API. So each type that you introduce forces the opinion on this has to be known at compile time. So if you are building a low-level API, forcing an opinion is not something you want to do early. So your lowest level needs to work with data. And then as you build abstractions on top of it, you can build more types on top of it. So a hypothetical correct evolution for us would be to, that's not what I wanted to say. You can think of Volcano as well as an example which goes type first. And I don't think you can build a lot of abstractions on top of Volcano because of that. What we should have done instead is to make the type layer the higher level and then untype the lower. So change the layers in the opposite direction. Then this is a wonderful thing. We had a concept of the pipeline, and by that time we already heard about the pipelines coming in Vulkan and Metal, and Vulkan wasn't even released at that point. So we thought users are going to specify everything, and we're going to call it a pipeline, and then we're going to build the Vulkan backend and Metal backend, and we are totally ready for the next gen. But we only had OpenGL at that point. So the concept of the pipeline was pretty far-fetched. We got the DirectX 11 later, but never did we get Vulkan on GFX pre-low level. We did get some of the Metal stuff, but it wasn't well tested, and nobody used that, basically. So the lesson from it is there are more things that prevented us from adopting the next-gen APIs. And what we should have done is designing for APIs that we know. So either stop designing and learn what you want to design for, or just ignore those things that you don't know about. This is the advice that you can find elsewhere. It recently showed up on Hackers News and stuff like that. Do not design for unknown future. That's our fourth lesson. Then we had this interesting issue, one of the earliest one, about the shading languages, that we needed some kind of shading language. And gfx-rs thought, okay, we are just a library. The user may use their own shaders to work with us. Maybe that's going to work well. We didn't know. We didn't have a good solution for that. And this is one of the oldest issue in the project from 2014. And it turns out that it's really important. People do not need reusable components. Developers need reusable components, but people need exact solutions. So if you are building a solution for something like a graphics obstruction, then you have to think about it top down, like everything needs to be covered. And just leaving the part of the solution as the shading language support completely aside means that it's not going to work. So for us, it meant that nobody except a few people used the G3D11 backend because you had to provide separate shaders for it, and we didn't have any mechanism to do that. And the interface was interesting, to say the least. That what are the expectations for those HLSL shaders? Okay, so we realized all the shortcomings. We realized we're not ready for next gen, and then Marcus came on board and basically started rewriting GFX. And we converged to an idea in 2017 that we can just be the lowest level API without any overhead, and people are gonna build higher level abstractions on top of us, and that's gonna be wonderful. And we love Vulkan, right? We appreciate everything that Kronos did, and we're gonna enroll totally in Vulkan portability. We were at the beginning of Vulkan portability, and we were playing a good major role in it. So we are gonna expose everything that Vulkan exposes just because we didn't know better. We are still learning Vulkan, like a lot of the industry at that time. We're still learning. So we thought it has subpasses, means that it makes sense. It has an explicit memory control, means that it makes sense. And everything has to be unopinionated. And we did that all within the same repository. So what could go wrong, right? So the result of that is that people are still confused what GFX is. They go to crates, they see GFX. They go to repository, they see an entirely different thing. And even though we're all developers, we have to think more about marketing and how do we position our products. So lesson for me, number 6, was that branding is very important for open source projects. And if you are building something new, try to have a fresh start, not rapidly like evolve everything and replace the code base in another thing. It's too much pain. And the transition rightfully killed most of the contributors at that point. Then we had the GFX hardware abstraction layer had separate backends in separate crates. And if you wanted to use a backend, you would hook up that crate and then use it as a generic parameter. So that genericness of the backend abstraction, it had to be bubbling up from the low level of the user code to the top, because there was no solution that would erase that. And rightfully, we didn't know what the solution is. We thought, okay, it's Rust. Rust is powerful. People are going to build something. Wrong. If you don't know how people are going to build something, then consider that people will unlikely build something. And people were just suffering. You would see the backend generic popping up to the top of the engines that user built, and it was confusing. Nobody wanted that generic there. Like you would see camera parameterized on the backend, for example. It didn't make a lot of sense, and it made the user-facing libraries not ideal. So if you don't know how users will solve the problem, and you know there is a problem, then it's your problem, basically. Okay, next. We know Rust has zero cost abstractions. Wrong. The zero cost applies only to optimized runtime at best, but there are other costs. This is the example of the vertex buffer binding. And the interesting things here are that we have two generics. We have I and T, and we have 3 different generic bounds on them. We have exact size iterator, we have the borrow, and that all was there so that we do least of work when users passed in their data. And we that was uniform across the whole GFX API. The signatures were huge, were complicated, and they were largely copied over between the backends. So why is there not zero cost abstraction? Because there are other costs. Like I mentioned, there is a debugging runtime cost. Like debug runtime gets slower if you have generics. Then there is a compile time cost and maintenance cost, which is very important for me as a maintainer, because there was a lot of code. We wasted a lot of time navigating that code. And for users looking at the documentation, figuring out why it doesn't accept what they pass in, they all wasted a lot of time. This was not worth it, I think. And that we did it all because we wanted zero overhead, but that zero overhead would only apply to Vulkan anyway. And even for Vulkan, there had to be some overhead because hash that we used received slices, and we need to get from iterators to slices. So it was small, but it was still some work. As an alternative, we should have considered more checks at runtime instead of compile time, I think. So receiving slices in some cases would be totally fine. Now, okay, we are gonna go and implement Vulkan on all the platforms. Do we know Vulkan? I guess we're gonna learn on the way, right? What can go wrong? So that's a lot of responsibility that we put on ourselves. And Vulkan is hugely complicated. As we discovered different parts of it, especially within the Vulkan portability side, we realized, and it was too late, that Vulkan is a huge machine. It has the tribal knowledge that different game devs know and pass to each other, but it's not like it's hard to dig up and understand. Why is it made this way? Because there is some obscure Qualcomm device somewhere that has hardware support for it. That's it. Like that's the reason, maybe, for why VK frame buffer is the way it is. So, and we decided to align with Vulkan because we didn't know best, and we became slaves of basically past decisions of the working group, Vulkan. We were at the bottom of the mountain. We knew that there are some independent software vendors that know much better what's going on, and there are people who write drivers, the hardware vendors, that know much better as well, and they make everybody's lives hard. As you can see, the lava flowing down. We were trying to get in touch with those hardware vendors to understand better, and as we were understanding it better, the illusion faded. The illusion that Vulkan is that API that exposes the hardware. It seemed that way, but if you actually look at the hardware is different. The hardware is very diverse. People make compromises, including the working group, and there are things that are just not very nice implemented in Vulkan because of the compromises. So Vulkan itself is not zero cost. Trying too hard to abstract over Vulkan and provide zero cost between an application and Vulkan is wasted because Vulkan itself will have some overhead on the hardware. So there has to be some trade-offs. The lesson from here, lesson number 9, is that one has to recognize the wishful thinking in the assumptions that they make. Our wishful thinking was that Vulkan is the best thing out there and is developed in open, in collaboration. It has to be good. That's what we assumed. It has to be good. And that was a mistake because in some situations, the big working group cannot efficiently make decisions. And it's much easier to have smaller groups, maybe behind closed doors, just with a good feedback loop from developers, with a good means of putting pressure on the hardware vendors. A different group may make better decisions. So there are a lot of things that D3, D12, and Metal got better, in my opinion, than Vulkan. Like an example could be the copy alignment in Vulkan, which it says here's the optimal one, but you don't have to use it. And if you don't use it, then the driver can go nuts and just generate a bunch of copy code for you, like copy row by row, which is not the best, frankly speaking. Yeah, so blindly following Vulkan meant that we had the deficiencies of that API. Okay, here's the evil plan. We're going to take Vulkan, we're going to implement it everywhere, as I mentioned, and users are going to be served by somebody else, right? By somebody else. Reminds you of something? There was an earlier slide in the Prelow level where we said that if you don't know how the user are going to solve the problem, then it's your problem. So this is basically the same thing. We tried and tried time after time. We tried to build a high-level abstraction. We had several prototypes. It failed. We didn't have enough knowledge. We didn't understand well how the users are expected to interact with an API. And everybody could try that, eventually crashed into the complexity. They would ask a bunch of questions. We would follow them to the Vulkan spec. And they would get lost in there because it's the Vulkan spec. So the lesson is very similar to what we had before. Take a particular need that users need solving and solve that. It doesn't have to be a low-level reusable component. So if we know that the need for the users is they need a good abstraction that runs well on the modern hardware, then we had to build that abstraction. So ideally, we would start by building wgpu. And then if we see that, oh, there is some part of it that can be moved out, then we would move it out into something like gfx hardware abstraction layer. That would be the proper evolution for it. Because what we did, we built the foundation without understanding what's going to stand on top of us. We thought users are going to be able to build abstractions over Vulkan. That's not so easy. And a similar lesson is that if you're unopinionated, it's not a feature. It's just a way to build higher level abstractions. But users don't care. If you end up finding or building a good high level abstraction that users do care, then what happens is that the needs of that high level start to drive the requirements for your low level. And then it also becomes opinionated. So no matter how you look at it, building something unopinionated is very, very tricky. So unless you really know what you're doing, build something opinionated and serve particular use cases. Finally, the sub lesson here is the smaller the API surface for the thing that you're building, especially if it's a low-level API, the easier it is for user to pick it up and build something on top. Like if you're building a file fetching API, it could be like one entry point. You can expect people to pick it up. But gfx-hal is a huge API, a humongous API. So nobody was able to build on top. All right, so was it all bad and we didn't have anything running? No, we did have some stuff running. In particular, we had the gfx portability. That's the project of wrapping gfx-rs into a C API that implements Vulkan. It's exciting. We were heavy contributors to Vulkan portability, almost driving it at some point. We ported the conformance test suite on macOS first. We benchmarked gfx portability by actually running Dota and Dolphin emulator on macOS over our library. And then we beat Molten VK in performance, although Molten VK is older and it's used in production. So success, right? Well, not exactly. People didn't care. They didn't. People just linked to Molten VK. They wanted to forget about the problem of running on macOS. Nobody wanted to think too much about it. Like, is there a solution? Yes, there is a solution. I'm gonna just bundle it with my app and forget about it, basically. And here on the left, you see me screaming with Lunar G, who wanted their loader to be used, but people didn't care about the loader either. Rust users didn't care about the C APIs. They would use Ash or something, and then Ash would come with the Molten VK wrapper, and they would pretend that it didn't exist and they are running on top of Vulkan, even though it's horribly unsafe and it's slow and like, they should feel bad. But that's what people do anyway. And C users just needed something that they can make sure survives. And gfx portability did not like something that can easily survive, and it didn't. So we fought against the flaw, and that fight was hard for us. We did a lot of success. We had a lot of success with this, though. It was fun. Profiling Dota in particular was very enlightening. So, but nobody woke up in the morning and thought, "Oh, I have a Vulkan application. I'm gonna make it run great on macOS." Nobody did that. Nobody cared. Okay, like speaking of good things, we had a lot of contributors. We had 1 byte of contributors basically, and 65K lines of code. Great. We had our own testing infrastructure. We had the 6,000 commits and growing, and a lot of stars. And with all of that, we had basically 1 maintainer at that point. That was me. And doing this was hard. People would come up with huge chunks of API that would work on very selected pieces of hardware or platforms just because they wanted to play with it, rightfully. But they would contribute and then forget about it. So I would be left with all the heaps of code that I need to maintain between the backends and the Vault. And that was not the best experience for me. This is the funny slide that Chronos Vulkan portability subgroup wanted to present to show how the stars are growing, the popularity of Molten VK and Spear Cross. And when they realized they needed to add gfx-rs to the story because we implement Vulkan portability, and gfx portability project is just a wrapper, so we added the gfx itself to the graph. It turns out that we dominate the graph. So, oops, I guess. But in the end, it doesn't matter. Doesn't matter at all. Your contributors, your star count, it's all secondary. You can't expect anybody to maintain their code. And the only thing you can do is have a small scope that solves particular task. That's the best you can do. All right, so where are we now? As of this summer, which ended just recently, we put gfx all in maintenance mode. And it is basically rewritten as wgpu all, as the thing that serves wgpu specifically and could be seen as an implementation detail of wgpu. So we are trying to learn from our lessons, and it takes a lot of effort. We're trying to keep it simple to solve a particular task, and it turned out to be great so far. We had almost 3 times less code. We had faster compilation times. We don't have any C dependencies anymore. and we follow wgpu API. And the difference here is drastic because unlike Vulkan, webGPU is designed to be ported over other APIs. So it's designed so that we don't have to have the crappy workarounds for the subclasses. It's designed so that the features that are not implementable are at least optional. So it's a pleasure to work with such an API at the wgpu level. And what's coming next? gfx-rs is, you can say it's dead, but the ideas live within the wgpu today. We are still thinking what to do with the portability project. We will appreciate any help for this. There's a bunch of links people can read for more context. Some of them are my blog and gfx-rs blog. And appreciate everyone tuning into my talk. Thank you. Please follow up with questions. Yeah, I forgot something to introduce myself. I'm Dmitry, and I've been doing Rust for a long time. And I currently work at Mozilla, but everything that you hear here, most of the things are unrelated. So that's everything.
My mic is a bit quiet on stream. Okay, test. Okay, I gotta turn my gain up pretty high. I think. Does it sound all right? And I'm just looking in chat. The host mic is a bit quiet. Yes. Is it better now? Now it sounds good. Okay, cool. All right, so we have a few questions that I'm just going to go over with you, Kvark. And so, first off, I was sort of wondering when you were describing branding in the past, what type of steps have been taken, sort of like towards more recent gfx-rs to help with branding, whether it be like blogs or just other stuff.
Right. We did aggressively post on the blog and saying how things are changing, but expecting people to always look at the blog. Like some people were fine with this, but most people did not look at the blog. And we did put a blurb at the top of the README as well, and that still wasn't enough either.
Okay, yeah, and so I think going forward, I definitely love seeing the new like sort of graphs that show the entire ecosystem, but I really like that idea of defining what it's what the purpose of it is. Um, all right, next question. So, on the topic of zero cost abstractions, I think this is around like lesson number 7. Someone asked, would it have been possible to streamline that level of genericness if Rust had module level type params?
That's an interesting thing. I'm not sure, actually. I'm not sure how this would work.
Yeah, I think that was like more of a just open-ended kind of thought there. But of course, we all like talking about optimizations. And so finally, um, another question. What's a good random example where Vulkan is awfully far away from the hardware?
Um, yeah, so I brought the copy example where it's far away, but I think there is a better example with descriptor heaps. In Vulkan, you can bind different descriptor sets allocated from different pools. But if you know D3, D12, you can only have one descriptor heap of particular type active at the moment. So it's much more restricted than Vulkan allows. And we were wondering, like, how do you guys implement Vulkan if you're so restricted? And it turns out, via a bunch of workarounds. Like we just copy descriptors in the driver when you bind them. When we see that you're using a bunch of different pools and we can't figure out where to find all of them in the single heap, we're gonna create a temporary heap and copy them. Like, how are you doing this? You're encoding at that time. Well, some people just have to do it. So that's unfortunate.
All right. And then one more I'm wondering about. In the Discord chat, we've had a lot of memes about, I don't know, like Vulkan and stuff like that. But what I'm sort of wondering about is, when it comes to projects that you're excited about, for like you describe a lot of the work that you do as the foundational level for a lot of other things. What are some other projects you're excited to see using the work that you've done? Or and as an example, you described how like loading Dota could be like much quicker, but not as many people cared. Do you think that in the future there's going to be like a lot more like big steps that really show that this is a really great way to approach things?
I think a lot of the effort put into it is already paying up. So the other example did not get into any production, but the work we do on the shader translation, for example, it's already useful to people because they port their stuff on WebGPU, and WebGPU uses the WebGPU shading language, and nobody writes in shading language today because it's not even stable yet. But Naga, our project of shader translation, allows you to get your GLSL and convert it to Wixel right away. And people use it. And it gives me a lot of pleasure to understand that like it's actually useful today, even outside of the WGPU ecosystem. And the WGPU itself, I think it serves well in Veloren and Bevy. And these are two projects I'm hugely excited about.
Awesome. Well, thank you very much, Quark, and we'll be back in just a few minutes with the next talk.